Hello, my name's Gokul, and today we're going to go through the 9th exam prep worksheet for 188. So I think this is the longest and hardest worksheet we've ever had, so it's quite challenging, but we'll do our best to get through it together. So let's take a look at the first question. So this question is focused on hidden Markov models. So in this question, we considered a process where there's a set of discrete states that you transition between. And the way these transitions happen is you stay in a certain state for some amount of time, and this duration is sampled from some distribution P sub d. And then after that duration is over, you transition to a new state. And which state you transition to is dependent on this distribution here, this conditional distribution. And this process just keeps running and running, and we have a bunch of questions about doing inference about this process, figuring out, what state we're in, how long we're going to be there, and so on and so forth. So let's take a look at the first part of this question. So assuming that these states are different, what's the probability of this sample sequence? So given that states are different, we know that there was actually like a break here and a break here, in the sense that we sampled from the state transition distribution and then stayed in this state for some number of steps. And let's write out this algebraic expression. So we're given some distribution over start states over here, this P1. So we're definitely going to have a P1 of S1 for where we start off. Then, how long do we stay in S1? We stay in S1 for 2 time steps. So we're going to need to multiply this by PD of 2, because we stay there for 2 time steps. After that, we transition to state 2. So for state 2, we're going to have probability of, let's see, we call it P sub t of S2, conditioned on being in S1. And we stay in S2 for 3 time steps. So we're going to multiply in PD of 3. After that, we're going to transition to state 3. So we're going to need to multiply the probability of transitioning from state 3 conditioned on being in state 2. And then we have to multiply the probability of, being in state 3 for at least 2 time steps. So if you take a look at this here, we don't necessarily just stop staying in state S3 after this. We only observe the first n time steps. So we can't just multiply in P S3 of 2. All we know is we were there for at least 2 time steps. So the only amount of time we could be in there less than 2 is 1. So all we know is that we weren't there for 1 time step, but we could stay for any number greater than 1 number of time steps. So what we multiply in is 1 minus the probability of staying there for just 1 time step. And this covers, 2, 3, and all the other things we might not be able to see. So this gives us our probability distribution. So what we did here is we know we start off with some starting state, we stay in from some distribution, we sample from transition distribution, we stay in this state for some time, sample transition distribution, and then stay in this state for some time. So there's 2 kind of steps to this process. One is staying in some state for some number of time steps, and the other is kind of moving on to the next one. So let's take a look at the next 2 parts of this question. So we were saying, okay, so let's say we have some states here and our observations here, and we only look at the observations for this part. But what we want to find is the maximum index such that, our start state and our current state are independent, conditioned on basically getting information from this index all the way up. So if we increase the index more, we get less information because it's kind of the starting point here. That's why they're asking for the maximum index. So let's think about this. What do we need to know kind of what's going to happen next? Well, we need to know 2 things. We need to know, basically, what state we're going to and how long we're going to stay in that state. And the only way for us to know this is to actually observe this transition between states, to basically see that, okay, I've jumped to a new state, and I've resampled from this distribution of durations. So we need to get both of these pieces of information. Once we know these things, then, okay, it's fine. We can kind of figure out, we can just kind of sum everything else out and it'll be just fine. But we need to know these pieces of information. If we don't know these pieces of information, we could be in this state for an arbitrary amount of time, and we have no idea of really figuring out whether we've transitioned or not, or other things. So we're given in the problem that there is some m. And this m here is the max amount of time we could actually spend in this state. So if we observe at least m time steps, that means we must observe at least 1 transition. And if we observe at least 1 transition, then we can sort of figure things out. We just need to observe the last transition before, we kind of reach step n. And if we observe m, we're guaranteed to observe this. So the I we should start from is I equals n minus m, because this will make sure we're able to reach the last, we're able to observe the last transition. If that was a bit confusing, let's take a look at the next part here, which I think makes it a bit more clear. So for this question, we're saying, okay, xi can only take on two values, we can only have duration for 2 time steps, and we have all of these here. So let's try and draw, basically the minimum base net that actually can capture all the dependencies. That's what this means. So, we start off with our x1, our x2, our x3, our x4, and our x5. And we have some distribution here, the probability of yi conditioned on xi. And, that means that each of the y sub i is dependent on its respective x sub I. So we can write out the y's, y2, y3, y4, and y5, and then connect these, because each of the y's is directly dependent. Then the other thing we need to worry about is the interdependence between the x's. So I think the more obvious case is that each state is dependent on the previous one, in the sense that we either stay in the same state because we haven't exhausted our duration, or we move to a different state. So let's connect these together. So we have each one of these dependent on the exact previous one. The one that's a little bit harder to get here, I think, is the fact that we can also say the same thing for 2 states. And that means we're not just dependent on the previous state. We also depend on the state before that. So we're not first order Markov anymore. So it means we could be dependent on states as far as 2 states back, because that could affect the state we're in, because we have this kind of conditional distribution over what state we end up in. So that means we basically need to have edges like this that reach 2 states back. And that's why we need to observe from I equals n minus m. So we can observe basically the thing that's encoded by these edges. And potentially this could not be important. For example, if this over here was ended up the conditioning didn't really make a difference, this might be less important. But given this is all we know, we do need to actually observe this part. All right, let's go ahead and take a look at the next few parts of this question. Okay, so taking a look at the next part of this question. So here we've said that, okay, before we haven't really kept track of the duration in any sense. It's kind of just like, it's just been like a floating number out there. But it seems that, we could just augment our state space and have this duration included in it. And that would kind of make this problem a bit easier. So what we're going to do is we're going to make our states the state we're actually in, our x sub I, as well as the kind of amount of time we've spent in this state. And this is a bit of an odd convention, the amount of time you've been in there versus the amount of time you have left, but it ends up being useful for some stuff down the line. So our state sequence from before will be represented like this, where basically, this number, the second element, the tuple, increments over time. So let's go ahead and write out this stuff here. So the probability of being an x1 for time t1. Okay. So, if we've been in this state for 1 time step, what's the only amount of time we could have been in this state is for 1 time step. What I mean by that is if t1 was anything but 1, this distribution should have probability 0, because it's the starting distribution. We've only been in there for 1 time step. So we end up with 2 cases here. So one case is that, we get p1 of x1, which is a distribution we're given, if t1 is equal to 1. Otherwise, we end up with 0. Because if t1 is anything but 1, given it's like t1, it can't be anything else, because we've been in this state for 1 time step, and we haven't been in for more than 1 time step, so it's got to be 1. So we have a similar kind of case-by-case behavior for the second part of this one. So if you remember from the other description of this process, there's 2 things that can happen. One is you transition to a new state, basically reset your duration counter. And the second is you stay in the same state and kind of increment or decrement, depending on your convention, the time counter. So let's take a look at this part. So let's consider first the case that we actually just stay in the same state, and we just increment our duration counter. So that means we're going to have a form like this. So x of I plus 1 is going to be equal to x of I, and t of I plus 1 is going to be equal to t of I plus 1. Remember, because we're counting up here. And then we also need it for t of I plus 1 to be less than or equal to m, because we can't stay in the state for more than that duration. And if all of these things are true, then we can define our transition probability. So our transition probability, we need to think about what we know and what we want to get. So given that we know we've been in this state for at least ti time steps, we know the duration has to be at least ti, because else we wouldn't be in this state for this long. So we definitely have to include that. We don't have just no information. We're not sampling from this unconditional distribution. And for us to stay in this state for longer, we do need to have at least enough time that we stay in this state for one more time step, for this current time step. But we could also stay in it for longer. This is kind of like what we had in the previous part, where we had the 1 minus thing, because we only needed to stay in this for one more time step. It could stay in it for more, but that would still be, consistent with what we're trying to look for over here. So the way we write this out mathematically is saying, okay, we want the probability that d is greater than or equal to ti plus 1. So we'll stay in this state for one more time step, conditioned on d being greater than or equal to ti, because this is the information we already have, given we've already been in for ti time steps. So that's how we write out this probability here. So this is basically, using what we know, and basically this is the minimum, the minimum condition such that we will stay in this state for one more time step. So let's consider the other case. The other case is we actually, move to a different state. So if that's true, it's going to look something like this. We're going to have xi plus 1 not equal to x sub I, and kind of like what we had in this case over here, we're going to need ti plus 1 to be equal to 1, because we just moved to a new state. And if this is true, we have another probability here. So the first probability we're going to have is okay, the probability of going to this new state, xi plus 1, conditioned on being in state xi. Sure. And then the other thing we need to worry about is the actual, the fact that we are actually done with our transition. So we need to actually multiply the probability that we've, exhausted out the duration here. So this distribution here is a bit tricky, but let's think about this. So we're definitely going to want the probability that d is equal to, t sub I, because that means, okay, we've finished off our time, we're going to move to a new one. So we need that in there. But we also need to include the information we already have. And the information we already have is that d is greater than or equal to ti. So this is definitely a bit tricky. So let's break this down one more time. So over here we have the probability that, we move to this new particular state. And then we have this probability that we've actually finished staying in our old state. So that's over here. But we also have to incorporate the evidence we already have, that d is greater than or equal to ti, or else you wouldn't be, using all the information we actually have. So we end up with this thing over here. So if this is true, we end up with a distribution of this form. And then, these are the only two things that can happen in our process. We either move to a new state after exhausting our distribution, or our duration, or we stay in the same state and for one more time step. So other than this, we have 0 otherwise. We basically have these 3 cases. So a lot of these transitions between some xi, some ti, xi, and some ti are going to be kind of with 0 probability. So we'll see later in this question we can use that to write a more efficient kind of update. But for right now, hopefully this form makes sense. There's 2 cases, and otherwise nothing else is possible. So lastly, we have this one over here, the probability of y sub I conditioned on z sub I, which we can break into x sub I and t sub I, because z is equal to these 2 things. So here we're given this distribution of p equals x sub I conditioned on t sub I, and sorry, that didn't make sense. Sorry, the probability of y sub I conditioned on x sub I, and we already know this piece of information. And if we look at this over here, this doesn't depend whatsoever on t sub I. Like, the observation we see, the y sub I, depends nothing on the amount of time we've been in this state. So we can actually, because it's conditionally independent, we can just write out that we have the probability of y sub I conditioned on x sub I. And we don't really need to worry about the t sub I there, because it's conditionally independent. All right, so that was this part of this question, quite a hefty part. Let's go on to the next part of this question now. All right, so let's go ahead and take a look at the last part of this question. Yeah, it's quite a long question. So for this one, we're going to actually, figure out okay, given all these like tables and conditional probabilities we have in our like hidden Markov model, how do we actually compute what we want to know, which is the state we're currently in given our observations. So for all of these sorts of filtering algorithms, they all have a really similar structure, where basically what you do is you write them recursively in terms of the previous version of this thing, x t minus 1 conditioned on yi to yt minus 2. And once you have that, you basically take that, multiply in your transition probabilities, your evidence probabilities, and you just sum out over the past versions of the things you're looking for, the query variables. And then you also sum out over basically anything you don't care about in your final expression. So that was a bit vague, but I think going through this example will help make that a bit clearer. But everything basically has that same form, where you have some recursive old version of what you're looking for. You multiply in some updates based on your transitions and some updates based on your evidence, and you sum out over both old versions of things and things you don't care about in your final expression. So for here, we have two things we have from our kind of old version. The first of those is the state we end up being in our last time step. That's what we sum out over here. The next thing we need to do is sum out over, durations, because that's also kind of part of our state. Remember, our state here is both x and t, and that fully defines our model. But then notice over here that we don't have any sort of t. We're not looking for the duration here. We just want the state. So we can also just sum out over that to drop it from our expression. So we can sum out over all three of these terms here. The next thing we're going to want is basically to have our sort of recursive term in there. So our recursive term, as I mentioned, is going to look like this here, where we have basically the same expression as we have over here, but one time step back, and without the actual time step included over here. That's what the summation over here, or the summation over d prime does. It kind of removes that. And the way we actually get our d prime is we have to actually do our transition update. And that's what this term over here is. So we go from our old state here to this new state here. And we basically can sum out over the d prime over here with this over here to basically get something of this form. So we kind of keep track of this kind of extended state, and then to actually answer the question we want, we sum out over the thing we don't actually care about. That gives us kind of this expression over here. So the form here is what we'll see kind of also for all the parts of the next question, this basic form, where we have some recursive term over here, we do some observation update, and we sum out over old things and things we don't care about in our final expression over here. So now let's take a look at the last two parts of this question. So the first part asks, okay, how much time is it going to take to actually do this summation? So let's see. So we have two sums over m here, and one sum over k. So we're going to definitely have something that's going to be proportional to km squared. But if you notice over here, this is for one particular x sub t. And there's up to kx sub t's, because we could be in any of these k states. So this expression over here is for one particular state we could be in. So we have to multiply this by one more k over here to basically get our k squared m squared thing. So this ends up being quadratic in basically the size of our state space, because our state is k by m, and we're basically summing over all possible things from the previous state to the new state. So our state here, once again, is both the amount of time we've been in there, as well as the actual x we're in, and we sum out over all possible transitions here. However, if you're remembering from the previous part, I was mentioning how a lot of these state transitions are actually quite impossible, because there's only two things that can happen in our process. We can either stay in the same state, or we can jump once our duration is done. And because those are the only two things here, a lot of these transitions have zero probability. So that's what this question is getting at here. It's saying that, okay, we actually have a very sparse transition matrix in the sense that a lot of the entries are zero. So can we use that structure to make our update a little bit more efficient? So let's see. So if we stay in the same state, that means we only have to sum out over basically durations that we could, that would, keep us in the same state one more time. And there's only m durations. So we're going to have like an m over here. And we have to do this for all k states we could be in to compute it for the full table. So we end up with the same state, this km term. If we actually change states, we end up having something like this. So we're going to be in some state k, and we could be in any of these states, and we have to sum out because we're going to go to a new state. And we have to also multiply in an m term here. Because if you remember in our actual form for our transition distribution over here, right, we also have to multiply in this term over here for basically the duration actually finishing. So we have to sum out over all those durations here, and that's why we get this m term over here. And the k term over here is for basically all the new states we could end up in, so this term over here. So once we have those two, we also need to, just like in the previous part, basically multiply by k, because we have to do this for all states we could end up in. So basically you have these two things, and then we do this for all k states we could end up in. So then our total running time will be O of km plus k squared m. And the way we would actually implement this is we would, just have some sort of rule that says, okay, like what we have over here, we basically have this like if statement, and we would basically not have to do these summations if we'd say, okay, if this is true, do the summation, or else if this is true, do the summation. Otherwise, just skip it. And that will allow us to basically skip a bunch of extraneous summations where there'll basically be a 0 multiplied in, so there's no probability of it happening, so it's not really worth doing. So these terms here are we can break them down into two cases. One is, based on duration, and then we can we have it do it for every state. One is based on both duration and the state you're in, state you moved to, and we have to do this for every state. That gives us these two terms here. And we add them up, and that gives us our big O bound. All right, yeah, this was a really hard question. I think this is definitely harder than most questions I've seen on exams before, but I think it's also a really good question because I think it gets at some of the core of the material in a way other questions don't. But yeah, this seemed like particularly challenging. Yeah, I get it. I remember I was going through this question discussion, and I was like, oh my god, this is really scary. So thanks for sticking with us so far, and we'll move on to now the second half of this worksheet. All right, so let's take a look at the second question. Particle filtering apprenticeship. Fun. So we have this problem over here, where basically you're observing actions. You don't observe states. And you want to figure out what the policy is. So basically you're trying to figure out, okay, this agent is executing one policy out of a set of policies. We want to figure out what it is by observing its actions. The thing we don't know, though, is remember, a policy is a distribution of action conditioned on state. And we don't know the state here, so the kind of hidden part of this problem is the states. That's why they're not really shaded in here. So let's take a look at this problem. So for the first part of this problem over here, this ends up being like a classic kind of deseparation problem. So let's consider all the kind of paths we have. So we're trying to find out between ST and ST2. So that would be between this one over here and this one over here, if you just shift the indices over by 1. So there's a couple paths we can go to. One is just, directly through the states. One ends up going, down through action, back up through policy, through action, and so on. And there's other ones, that go through actions and so on and so forth. So for us to have guaranteed independence, we need to have no active paths. So what we need to do is basically block all possible paths like this. So let's take a look at these options. So if we just, observe ST minus 1, we still have a path through the policy over here. If we observe both S of t and A of t, we actually can't even get to the policy node over here because we've blocked off basically everything from S of t minus 1. So this will give us independence. If we observe just the policy, we could do it through the states, so that doesn't work out. And if we observe both the policy and the action, we could still go again through the states. So that still gives us an active path. So that doesn't work out either. If we look at this one over here, if we observe both the policy and this state over here, we can get to the action, but we really can't go anywhere from it because all the edges just go to, either here or they're here. And because these two are blocked, it's equivalently just being blocked. So this one also gives us independence. And for similar reasons, now if we also see the actions, well, it's just extra blocked. So I did that pretty quickly, kind of just based on, looking at things that were blocked. In principle, you should, go through the actual deseparation, but if you do that, you should end up with basically what I just got there, which I think is, probably fine. So now let's take a look at the next part of this question. So for all the other parts of this question, there's a pretty kind of like templated approach to actually writing out these kind of filtering approaches, both in the exact sense and in the particle filtering sense, because particle filtering is basically an approximate version of a perfect Bayesian filter, and we're going to go over both the exact version and the approximate version. But the important thing to keep in mind is these have like a very kind of like formulaic or templated kind of structure to them, because they're all trying to solve a very similar problem. So kind of making sure you kind of get what that structure is so you can kind of easily kind of just plug and chug in terms, I think would be really great. I think it's pretty hard to kind of come up with this stuff on your own, so just keeping the template in your mind is good. So let's go through the first part of this one. So we're going to have something that's proportional to this. So as I was saying before, we want to write out something like this, right? So the first thing we're going to do is we're going to sum out over old versions of something. So our old version over here is going to be the old state, so st minus 1. The next thing we're going to do is we're going to basically have our recursive term. So our recursive term over here is going to basically be the policy, pi, and st minus 1, conditioned on basically all the actions we saw prior to this, so a1 to t minus 1. And if you look at this, this is basically the recursive version of this, just one time step back. So okay, we're going to sum over these, but we also need to actually do our time-elapse update and our evidence update. So our time-elapse update, which is our transition function that we actually know here, is going to be s sub t. Wow, I didn't even know you could do that. S sub t conditioned on s sub t minus 1 and a sub t minus 1. And if you look at that, the s sub t minus 1, a sub t minus 1 determine the next state we end up in. So this is basically our transition update. And we multiply this to basically get our s of t, and then we sum out over s of t minus 1 to basically remove that term from our expression. So this is just like a general pattern you see. You basically have some transition distribution that basically move you to the next time step, and then you just sum out over the old time step to get rid of it. And if you think about it conceptually, what you're doing is basically saying, okay, for all the states I could have been in before that end up in this state, let me add up all those probabilities, which in principle should be a pretty sensible thing to do. And then we also need to include our evidence here. So our evidence here is the actions here. So our action distribution, if we take a look here, is basically the probability of some action, a sub t, conditioned on basically both the state we were in, this s of t, and the policy pi. So we observe this over here, and so that ends up being fine. It ends up just multiplying in. And then we are okay with having this s of t and this pi here. And we get the s of t from over here and the pi from over here. So we don't have to worry about summing anything out. And then this basically gives us the exact expression we want, where we have something conditioned on all the actions. And we also have the incorporation of our new state, and we have our evidence being used, and we still keep this pi over here. So if you notice over here, we don't actually update the pi over time, because we're just, rather, what I mean to say is, we don't have like a pi of t thing. This is because if you take a look at it, pi is constant throughout the entire expression, through the entire process. We keep the same pi. So we just, as we get more and more evidence, we just update our estimate of what pi is. So this is a pretty common thing you'll see in like Bayesian filtering, where there's something you try to estimate, and as you get more and more evidence, you have some prior, you add in some evidence, you get a posterior, and that posterior becomes your prior for the next time step. And you just do this over and over, and you refine and refine your estimate. Here, what it is, we basically, are trying to figure out what our policy is, and we refine our estimate by basically observing actions, and then basically summing out over all these other things over here to try and get us kind of a useful thing here. And this basically gives us our algorithm. And I think that we call this the forward algorithm in this class. So the templated approach here is basically saying, okay, we're going to, sum out over states that we could have been in previously. Then we, look at our recursive term, we look at the transition, we incorporate our evidence. And then this basically gives us a term that's proportional to what we want. So this is a kind of like template I think you want to have in your mind. And we'll see this kind of play out again and again in the other parts of this question. But first we're going to look at kind of the approximate version of this. So let's go ahead and do that. All right, so now we're going to look at the approximate version of this, which is basically a particle filtering version of this one over here. So we're basically going to write this as a particle filter instead. So what this means is we're basically going to have a particle that is basically a sample that represents something that could be true. And we're going to have a weight for this particle that is basically how likely we think it is based on the evidence we've observed. And then what we do to do our approximate inference is we basically take our particle, we transition it forward by sampling from the transition distribution, and we re-weight it based on the evidence of what we just observed. And if we do this often enough and for a long time, we will start getting kind of estimates of what we want. And this is basically, if you want to think of it this way, it's basically kind of like chained likelihood weighting, where we basically do a likelihood weighting step at every time step. And then the chaining comes from the sampling from the transition distribution. So what we're doing here in filtering is very, very similar to what we did in sampling, but we're just doing it over multiple time steps. So let's go ahead and take a look at this over here. So kind of like I was saying before, we have our first thing, which is our time-elapse update. And if we take a look at that over here, that's this over here. So we're going to basically sample from this distribution over here, S of t conditioned on, S of t minus 1 on A sub t minus 1. So that's just basically this term over here. Can't draw across lines. Pages. Okay, cool. And then remember how I said we have just one estimate for the policy per particle? Because basically the policy doesn't really change. Our policy is the same over time. So we can basically initialize, all these particles with all these, n different policies we could be executing and just re-rate them over time. We don't really need to change between policies here. So our new policy is going to just basically be pi, our old policy. And I think we call it pi sub I here. And if you notice over here, our sample has both of these here, the S of t and the pi sub I. And that's because if you look over here at the exact term we're computing, we have both the policy and the state we're in. Because the policy, remember, is kind of state dependent, so we need to, or the actions taken by the policy are state dependent. So we need to actually include that in over here. So in principle, we could, have some policy that is, just pi of A sub t and it's independent from S of t, but generally that's not true, and we don't know whether that's true or not in this case. So we need to include our state there. So then, like I was saying, our actions here are our evidence. So to actually incorporate our actions here, we're going to have our A sub t conditioned on basically our S of t and basically our pi prime. So I think I'm one off by the time steps here, but if you just shift all the times before one, you'll get the same kind of time indices they're using here. But we basically incorporate our evidence, our observed actions, and we basically, it's dependent on basically the thing we're moving towards. So this like new state and this new policy. But remember, as we said here, new policy is the old policy. So what we're doing here is basically saying, okay, we have some exact knowledge, at least in our particle, of where we're saying, okay, this is where we are. And then what we do, we say, okay, we're going to weight the probability that we're actually in this state, and we move to this new state based on the action we observe. So we say, okay, we're definitely in some state, we hallucinate that we're in some state st. And then we say, okay, we observe some action, what state will we likely end up in? And that's what our new state we observe is in. And we just assume that we're executing this policy all the way through because we end up having this one policy for the entire process over here. And that basically gives us our update here. And then, we have this weighted distribution, and we basically use our sampling trick to basically, sample from this weighted distribution, end up with basically, copies that are proportional to the weight. So what we do is we have, some set of weights, and we say, okay, if we have two particles, one with weight 0.6 and one with weight 0.4, we can basically sample from this distribution by, taking a uniform distribution and basically, checking if it's less than, 0.6 or greater than 0.6. We sample this from this a bunch of times, and then we basically get a bunch of particles with uniform weight. So this basically is because it's a bit annoying to keep track of weights when we're trying to do inference online, and this lets us basically kind of like remove the weights. All right, let's take a look at the next part of this question, which is pretty similar in structure to the previous part, just with a bit more evidence. So over here now we don't just observe just the actions, we also observe the rewards here. And the rewards here, unlike what we saw, in lecture and in discussion, are going to actually be a random variable. Because if we, if we assume it's perfectly deterministic between, states and actions, once you know those, your reward, then it could be, pretty easy to sort of figure out, what your state and action kind of hidden variables are. And we want to make this problem a bit more complicated. So we basically assume it's a random variable. So what we want to show here, okay, there still is some useful information here, because deseparation doesn't tell us that, this and this are independent. There actually is some useful information here. So what we want to do is basically show that there is useful information by showing that there is an active path. So we're not sure that it's independent. So once again, this doesn't guarantee that it's useful information, that we're actually, getting something here, but there's a chance it could be. So we're going to, go ahead on that chance. We're going to be optimistic today. So we're going to start off with pi. Let's see. We want to get some from pi to r of t here. Well, I guess one thing we could try and do is say, okay, we're going to go from pi to, let's say, a of t here, and from a of t to s of t here. And this right here is an active triple. And then from s of t, we could jump right to r of t, because, s of t influences r of t as well. And then this one over here is also an active triple. So we found an active path here. And that's all we need for this question. So just to write it out, our path would be, pi, a of t, s of t, and then r of t. Okay, so now let's, this part kind of finishes abruptly. Let's go on to the next part. Part C. So this is kind of similar, but instead of observing the actions here, we instead just observe the rewards. So for this part, basically we just have this one extra thing here where, both the states and the actions influence this reward, and we don't observe the actions here. So our formula here for the update and the particle filter is going to look very similar to what we had before, just with this extra term added in. And we're basically going to sum out over things we don't want once again. So let's write this out. So the first thing we're going to do is we're going to sum out over the prior versions of these terms. So because we have s of t and a of t here, we're going to sum out over s of t minus 1 and this a of t minus 1. We're not going to sum out over policies because that's what we're actually trying to estimate here. We still want that term. So we're going to basically have multiply in our recursive term here, our probability of pi, let's say st minus 1, or it should be st minus 1, at minus 1, conditioned on, r from 1 to t minus 1. So we have a recursive term here, which is the same thing as here, just one time step back. And then we're going to multiply in our transition function here. So the tricky part for this question is there's two transitions here. So the first is in terms of the state, which is, the probability of s of t conditioned on s of t minus 1, a sub t minus 1, which we had before. But now we're also going to have another thing we're going to multiply in, which is going to be the action we actually produce. Because here we don't observe the action anymore. So we need to multiply in this distribution here of a sub t, conditioned on s of t and pi. So that's because we're looking for kind of a of t in our final expression. We need to multiply this term over here. And notice it's a capital A sub t because we don't actually observe the actions anymore. But we do have evidence here. And our evidence here is in the form of rewards. So we can basically multiply in our reward term here and get something that looks like this. The probability of our r sub t, lowercase because we actually observe it, conditioned on the s of t and the a sub t. So this term right here is our evidence. These two terms here are our kind of time-elapse update, and then this is our recursive term, and we sum out over all the things we had before. And once again, it's the same kind of general form we had before, just with extra terms. And conceptually, I think this should be, not that it should be very clear and obvious, but that I think if you kind of ponder it for a bit, it should make sense. But what we're doing is we have this old term, and we're basically applying Bayes' rule to basically move it to this new version, and we're incorporating evidence to figure out how much we should weight it. So let's take a look at the particle filtering version of this one over here. So, and yeah, I'm quite sorry about how this is printed out. It's kind of weird that this is on a separate blank by itself. But let's see what's here. So, we have our two updates here. So the one is the probability of s of t conditioned on, s of t minus, oof, that was messy. The probability of s of t conditioned on s of t minus 1, a of t minus 1. And we also do the same thing for action. So the probability of a sub t conditioned on, s of t And these are a bit, I shifted them by 1 again, but I think it should be fine, and pi sub I. And like we said before, we're still just estimating 1 pi, so we're going to just keep the pi sub I there. It doesn't really change over time. And then we have to incorporate our evidence. Our evidence here is now our reward. So our term is going to be pretty much exactly what we had up here. We're going to have the probability of, R sub t conditioned on basically S of t and A sub t. So yeah, notice here how the action and the reward are basically dependent on the current values of S and A, while the state here is dependent on the past values. So state moves, and then it kind of helps produce these A of t and R of t with help from the policy. And that's why we have to have these two terms over here, because we actually need them to figure out what we're trying to look for. Okay, cool. Well, we have a long empty page. And now let's move on to the last part of this question. Or, no, it actually isn't the last part of this question. It's a very long question. Wait. Oh, actually, this is the last part. Yeah, this was an 8-page worksheet. It was quite difficult. But it's also, I think, a really good worksheet in the sense that, like, if you really understand these two questions, I think you'll be pretty good to go on anything we could give you on these two topics. And they're also, like, pretty useful in the sense that I think a lot of stuff in this class is kind of a more classical version of something that we have like a more modern update that we usually do. But this sort of stuff, particle filtering for like let's say like robot localization or something, is something that actually works decently well in the real world. It's actually, a pretty great technique. So I think like learning this is actually something really useful. And there's basically more complicated versions of this that are used now, but I think the connection is a bit closer than perhaps some other things we've seen in this class. So this is something beyond just doing well in exams. It's a useful use of your time to kind of invest to figure out how to actually do it. So let's take a look at the first part of this question. So for a fixed state action pair S of t, A sub t, what is this sum over here? Well, this is just the sum of some probability distribution. And we're summing over something on the left, and there's only one term. So yeah, it's going to end up being 1. This is just kind of, any distribution, whether it's conditional or unconditional, when you just sum out over all terms goes to 1, because, it's kind of an axiom of probability. So what are we actually doing for this question? We're saying, okay, we want to, observe, we're just going to observe the A sub t's. We also want to keep track of these R sub t's here. We're going to just kind of keep them in our expression. So we're going to have to basically kind of, incorporate, some terms that, are include of the form, R of t dependent on all the S of t and the A of t. But then for our final expression over here, we're basically going to sum it out. So if that seems a bit not particularly useful, you're right. Well, it's going to be equally accurate because, if we're already worrying about the A sub t, knowing the R sub t doesn't really help us here. We observed the A sub t. So, yeah, you're just kind of, basically adding in some term, and then you're summing it out, and it doesn't really add any more evidence to what you're doing. It doesn't really help you out. In fact, the only thing it does is just takes up more time. It's just equally accurate because we're observing the same amount of things. We're just adding in this term and then just summing it out. So it's almost like you multiply everything by 1/2 and then sum out the 1/2. So it's going to be the same thing basically. You have to do the extra multiply and sum out. So it'll just take more time, but it won't actually be more accurate. This question was a bit of a gotcha, but I think it was meant to be like something where you could just quickly answer it after the end of this very long and arduous journey. All right, well, that is this 8-page worksheet. Hopefully you stuck all the way through. This was really, really challenging, and I'm very proud of you were able to get all the way through this. I was super confused the first time I did basically every part of this worksheet. I think it's really, really challenging. But if you're able to understand all parts of this, I think you'll be in really good shape for the exam. So good luck studying, and yeah, thanks for watching.